Here's our last step in existence of covers, which is to identify correctly the cover we have constructed. So we have P from y0. Well, I said that, but that's not quite correct. We haven't yet got y0. We can take y0 to be the class of E. Okay, so remember y is the quotient of some omega hat of x semicolon x0. So we look at the quotient, we look at the class of E, which is actually ex0, the constant path that will give me an element in y0. It's a natural base point, it maps to x0, and we have these map. Okay, so the general fact from our correspondence between fibers and right cosets is p star pi1 of y0 is the class of all alpha, okay, of course, which is going to be a loop in xx0. So this was the class of alpha is the set of all g, so that alpha tilde of 1 is going to be equal to y0 itself. For a given curve, we have a uniquely defined alpha tilde. So this being a loop is exactly what these things are. So in our situation, so in general, this is in general. Okay. In our case, what is alpha tilde? Well, as usual, alpha tilde is unique. So if you get a correct description, so we have a path alpha from which we have to get a correct description, which goes from alpha of 0 to alpha of 1 of its lift. And its lift here is a family of paths which starts with a path at alpha of 0, ending at alpha of 0, and ends with a path ending at alpha of 1. And if you guess correctly, it's easy to verify, and you presumably have already guessed correctly that I can take alpha tilde of s is the map which will send theta in 0, 1, okay, to the function. So this is a path, so it's a map which will send it to alpha of theta times s. So if theta is 0, this is constant at alpha of 0. If theta is 1, this is alpha itself. Okay, and indeed at any given time, it is a lift of alpha. So if I look at alpha tilde of s of 1, this is alpha of s is going to be 1. So this is going to be alpha of s. Okay, there's a bit of a backward notation here because the role of s is different in the two places. Okay, so alpha tilde of s is a path, so it's going to end at some point, and that's going to be alpha of s, simply because theta is 1 in this case. So there's nothing complicated. Okay, that's great. So hence, what is this group p star of pi1 of alpha? Let's just say alpha tilde of 1. Okay, so this is simply, I'm sorry, I should correct myself here. This is going to be the class of these paths. It's not these paths. We are looking at equivalence class. So this is going to be just the class of the path alpha. Okay, and so hence alpha tilde of 1 is going to be y0 if and only if the class of alpha is the class of E. Okay, so which is alpha is a loop here. So this is only for loops. So this is not xx0. Similarly, here we have to take alpha as a loop, and alpha of this is equal to E. But I have to correct myself with this. It's not that it's equal to E. We have an equivalence relation that this is equivalent to E. This is equivalent to alpha star E bar, which is just alpha, is in H. Okay, so what does this let us conclude? So thus p star of pi1 of y0 is going to be the set of all class of alpha, such that the class of alpha, this is the class in the ordinary sense of homotopy class, belongs to H, which is H itself. Well, that's what we had set out to show, right? So all this is under the assumption that X is locally path connected, semi-locally simply connected, and connected. We have constructed a cover with the fundamental group being H, or more precisely the image of the fundamental group. Okay, we have done all our work now. All that remains is going to summarize the statement, what we call Galois theory for covers. So the Galois cover theory for covers will say that if I have G is equal to pi1 of xx0, and we take X is connected, locally path connected, and semi-locally simply connected, then covers P from Y to X, y0 to X. So let's not talk about covers first, let's talk about based covers first. So then based covers P from y0 to x0 correspond to the subgroup H contained in G, and furthermore we know that fiber corresponds to the right coset space. In particular, the cardinality of the fiber is going to be the cardinality of this. This is particularly important if H is a finite index, for example, or if it's infinite index, you know you have an infinite cover, and so on. Okay, so these are the based covers, and covers P from Y to X, they correspond to conjugacy classes of subgroups. We have both existence and uniqueness subgroups of G. Okay, so we have for each cover, by choosing a base point we get a subgroup, but this is well defined only up to conjugacy, and two of them are isomorphic if and only if they cover. But what's more is that we have deck transformations for a fixed, let's say, base cover. So they correspond to the normalizer in G of H divided by H. Okay, and these are transitive. If and only if H is normal in G. An important case of this is when H is going to be the trivial group, then the cover is the universal cover, and then you have deck transformation. So this tells you that you have a lot of symmetries. This is extremely useful that you have symmetries upstairs. Okay, this, of course, other uses of this is we can construct covers using this, and then use map lifting to lift functions, as we saw applications in complex analysis, and so on. So this is a nice description. We know all connected covers. If they are disconnected, then they have many components which are classified in exactly this way. Okay, they correspond to subgroups. We also know the symmetries of covers, and we know both the based case and not based case of these covers. Okay, so that concludes this abstract theory of covering spaces and fundamental groups, as well as some rich concrete examples. In this portion of the course on fundamental groups, there's really one topic left, which is how we have fundamental group of a combination of spaces in terms of the given spaces. Okay, the so-called Seifert-Van Kampen theorem, and from that we will see more applications of various sorts.